Bismillahirrahmanirrahim. Dear students, welcome to the Electrical Engineering channel. In this lecture, I will discuss characteristics of DC generators. And first, I will discuss separately excited DC generator. Then, I will discuss self-excited DC generator. In separately excited DC generator, the first characteristic is the open circuit characteristic, and this characteristic is drawn between E naught and IF. And E naught is the output voltage of the generator at no load. And here you can see this is a separately excited DC generator, and we have a field winding over here. This is the armature winding, and no load is connected at the armature winding, and we will just connect a voltmeter over here. This voltmeter will read the voltage, and that voltage will be represented by E naught. And this is a variable resistor which is connected in series with the field winding, and that variable resistor is used to control the field current or field excitation. That field current will control on the magnetic flux, and with that varying magnetic flux, we can determine or we can check the variation of the output voltage. So if we increase the field current, definitely the output voltage of the DC generator will increase in a direct proportion, and this will be the variation of the output voltage at no load of the separately excited DC generator as we increase the field current. And if we increase the speed, then these characteristics will shift upwards, right? So this is at speed n1, at speed n2, this will be the variation of the output no load voltage, and this is the output voltage at no load at a speed of n3, and n3 is greater than n2 and n2 is greater than n1. So this field current can be varied by varying this resistance. If we increase the resistance over here, then the field current will decrease, and when the field current is small, we will have less voltage at the output, and E naught is the no load voltage. So if the knob of this variable resistor is placed over here, then maximum current will be flowing through this field winding. Similarly, if the knob of this rheostat is placed over here, then the voltage at this field winding will be minimum, and zero current will be flowing through the field winding, right? So with varying this variable resistance, we can achieve this data experimentally. Okay. So now we will discuss internal and external characteristics. And before discussing these internal and external characteristics, I will come back to these no load characteristics of separately excited DC generator. And in this case, you might have observed that at zero field current, still we are observing or we are getting some output voltage at the DC generator. So this small induced EMF at the DC generator output is due to the presence of residual magnetic flux in the stator poles, right? So the magnetic poles are made of ferromagnetic materials, and in ferromagnetic material, even if there is no external magnetic field, they retain very small amount of magnetic field in them. So the retentivity of ferromagnetic materials is very high, and the permanent magnets are also made using ferromagnetic materials, and even in the absence of external current through the windings, there is small magnetic field which is already present in the stator poles. Due to that residual magnetic flux, slight EMF will be available at the output of the DC generator, and when we increase the field current, that magnetic flux will further increase, and increase in the output voltage will be observed. So that was very important point. Now, internal characteristics and external characteristics are to be discussed. Internal characteristics are drawn between E and Ia, right? E is the induced EMF at the armature winding, and Ia is the armature current. And external characteristics are drawn between the terminal voltage and the load current. V is the terminal voltage which is available at the load or which is available at the terminals, output terminals, and IL is the load current. So at no load, the output voltage will be maximum, right? When the load current is zero, the output voltage will be maximum, right? And in that case, E will be equal to V. So E and V are equal at no load, and that is this point. So when load current increases, armature reaction increases, and when armature reaction increases, the net magnetic flux which is available will decrease. And as a result, the induced EMF will also decrease. So that's why at high load current, you can see that the voltage is reducing, and that reduction in the induced EMF E is due to the armature reaction drop. So BC is termed as armature reaction drop, and at the terminal, the output voltage available will be even smaller, and that VT will also contribute the armature copper loss, right? So VT or the terminal voltage will be obtained by subtracting the armature reaction drop as well as the armature copper winding drop or voltage drop across the armature copper windings. So these are the characteristics of the DC generator uh, between E and IA and V and IL, right? So this is IL. Now I will discuss the DC shunt generator. And in DC shunt generators, we all know that the field and the armature windings are connected in parallel. And this is a rheostat, which is a variable resistor. Here we have the armature winding, and this rheostat is used to vary the field excitation. This is the voltmeter which is connected in parallel with the armature, and we have an ampere meter also over here, and this is the load impedance. So here again, this is our no load voltage. As we increase the load current, we will observe a reduction in the output voltage. And these are the internal characteristics, these are the external characteristics, and clearly the induced EMF will decrease as IL increases due to the armature reaction drop, and terminal voltage will reduce further due to the voltage drop across the armature windings. And if we go on increasing the load current, or we can say if we go on increasing the load, then we know that if it increases beyond the rating of the DC generator, then the induced EMF will start decreasing further, and the load current will also start decreasing, and our characteristic will start shifting towards the left side, and here it will become zero. Okay, so here BC is the armature reaction drop, CD is the armature copper loss, and AC is the internal characteristics, and AD is the external characteristics. So let's discuss the DC series generator and DC compound generator. In a DC series generator, if we increase the load current, then it means we are increasing the armature current. And since armature winding and field windings are connected in series, so if we increase the armature current, then the field current is also increasing. And when the field current increases, the magnetic flux increases. And when magnetic flux increases, the output voltage or the induced EMF will also increase. So in DC series generators, as a result of increasing the load current, the output voltage of the DC series generator also increases. So these are the characteristics of the DC series generator. Here E node is the no load voltage. EG is the generated EMF in the armature, and EG is smaller than E node because EG is the induced EMF at load, and E naught is the induced EMF at no load. And this difference is due to the armature reaction drop, and VT is the voltage available at the terminals of the DC generator, and this voltage is even smaller due to the voltage drop across the armature windings. So BC is the armature reaction drop, CD is the armature winding drop, and OD is the external characteristic. Okay, so OD is the external characteristic. So these are the characteristics of the DC series generator. And if we check the characteristics of DC shunt generator, we can see that as a result of increasing the load current, output voltage decreases. And here, as a result of increasing the load current, output voltage increases. And in compound generators, compound wound DC generators, the induced EMF will be lying between shunt and the series generator cases. So it will be fairly a straight line as a result of increasing the load current. And this is one characteristic, right? This is another characteristic, and this is another characteristic. AB is called over compound. And in this characteristic, we can see that the net increase in the output is observed as a result of increasing the load current. So in this case, it means the field winding which is connected in series has higher contribution, or we can say that the inductance of the field winding connected in series with the armature winding is higher as compared to that field winding which is connected in parallel. So the series wound DC generator has more impact, right? Because the DC compound wound generator is established by connecting two field windings with the armature winding, and out of those two field windings, one field winding is connected in parallel with the armature winding, and one field winding is connected in series with the armature winding. If the inductance of the winding connected in series is higher, then we will get such a response. And if the inductance of the field winding which is connected in parallel with the armature winding is high, then we will get such a response. And if the inductance of both the windings uh, is equal, then we will get fairly a straight line, right? So this case AB is called over compound, AC is called flat compound, and AD is called under compound. And that is all about our today's lecture on characteristics of DC generators. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.